4.5 billion years, the Earth has been blasted, burned, ripped and scoured. These phenomenal events have sculpted our planet through a series of devastating cataclysms. Our ancestors thought volcanoes were the doorways to hell. We think we know better, but we still live in a world driven by natural forces which we cannot control and which are indifferent to our needs. We hope the earth beneath our feet is still, but that is a deception. We live on a restless planet. We're only just beginning to understand the awesome power that can raise mountains, form the continents, open and close the seas. We are learning more all the time about the forces that drive our Earth and how to live with them. But it may be too late. The geological truce between ourselves and our restless planet may be coming to an end. '79 AD, Pompeii, Italy. A peaceful Roman city was overwhelmed by pyroclastic fires from Mount Vesuvius, a volcano that had slept through recorded history until it suddenly exploded. 20,000 people lived in Pompeii. Very few escaped the volcanic shroud. 2,000 years later, the people of Montserrat, a small Caribbean island, faced the same threat. In June 1995, the volcano of Soufriere burst into malignant life. It had been dormant for 400 years. Nineteen people have died, and half the island is uninhabitable. Where once there was a green forest is total devastation, an ash desert. Scientists from all over the world are trying to forestall an even greater disaster.
What we're looking at here is the Soufriere Hills volcano. And basically what it is this big scooped valley. And part of this valley is what we call English's Crater. And that's that big amphitheatre. Sitting within the amphitheatre is the present active dome. And basically what happens is that the magma is pushed up from below, and it comes out, it's exceptionally viscous, and it just fills up and up and up, forming this big dome structure. It's exceptionally hot, very unstable, and these blocks that are overhanging is what usually falls off, generates the rock avalanches, and then the pyroclastic flows.
Mark Davies can't just watch from the safety of the helicopter. He must get as close as he can to the flow. It's incredibly dangerous. At any moment, and without warning, the volcano might erupt again, and he'd have no chance of escaping.
We're quite close to the dome here. You can feel the heat coming off it. So it's not really a place we want to hang around. The cracks have opened up 6 centimeters in 3 days. So we'll have to keep an eye on them.
A pyroclastic flow is essentially like a snow avalanche. The only difference being that it's around about 800 degrees C. It contains big, huge blocks within it, sometimes the size of houses. It contains lots of poisonous gases, and all of that will travel at around about a speed of 80 meters per second in some cases, sometimes a heck of a lot faster. So you can't outrun it, you can't outdrive it, and in some cases the only thing that can get you out fast enough is a helicopter. Essentially, if you get caught in a pyroclastic flow, you really don't know whether you'll get crushed, whether you suffocate, whether you burn to death first, and frankly, I wouldn't want to know myself.
This is how Montserrat used to be before the catastrophe. An 8-mile paradise with green hills and tiny farms that had crept close to the mountain. The towns were full of memories of the colonial past. Now all that has gone. Sometimes ash falls like hail for a day at a time. The heat can be felt a mile away. The smell of burning sulfur fills the air. The sun is obliterated, and the midday sky becomes as dark as night. There is nothing to be done but take cover. Plymouth, the capital, was like Pompeii, a thriving port, center of island life. It too lay in the path of the pyroclastic flow. Because they had warning, the people were able to escape, but slowly their town is disappearing under the pitiless flows and remorseless ash. A volcano can sit quietly for centuries until the pressure from below becomes too great and it explodes. What everyone on Montserrat wants to know is, will it explode again, and will it ever stop? The scientists' best hope is to monitor the earthquakes they know will shake the mountain before an eruption. 24 hours a day, they listen and watch.
This is the operations center for the volcano observatory. It's monitoring the whole of the volcano. It's an early warning system, if you like. We have points all around the volcano, and so if the ground's moving, then the information that those machines gather out on the volcano is sent back here, and it's recorded on these pens. So it's a visual way of determining how much motion is occurring.
1 in 10 of us live near an active volcano. Many choose to because volcanic soil is so fertile and productive. But will the people of Montserrat ever be able to return to their fields and old ways of life? Or has that gone, as lost as Pompeii? People and politicians would like clear-cut answers, but scientists know that's impossible. No one can tell what a volcano is going to do next.
If the eruption stops tomorrow, the dome is still up on top of the volcano. It's still unstable, and it'll still retain its heat, and it might stay like that for 5 years after the eruption finishes. Or it might cool down exceptionally quickly, and within 1 year, people could move back. We don't really know.
Montserrat's disaster is caused by something that happened over 4 billion years ago when the Earth's crust broke into gigantic sections, forming the tectonic plates. They drift endlessly around the globe like giant bumper cars, joining and separating, carrying with them all the continents and oceans. The crust that forms on lava ponds behaves much like the plates. There are 9 huge ones, many thousands of miles wide, and it's at their boundaries that catastrophes occur. Montserrat sits on the boundary of the Caribbean and North American plates, where volcanoes erupt and earthquakes shudder. When they clash, new landscapes are created. Oceans shift, and mountains soar into the sky. "50 million years ago, the Asian and Indian plates were about to clash. Separated by a dying ocean, they collided with fantastic force. Neither would give way, and the land had only one way to go: up. This is the world's highest mountain range, the Himalayas. This entire area was uplifted from sea level to over 5 miles high in less than 30 million years. How do the scientists know? From the evidence of the rocks.
There's dramatic evidence for this uplift right in the face of Everest and Lhotse. The famous yellow band that you can see cutting across is actually a marine limestone. It was formed in the bottom of the ocean.
So 50 million years ago, the tops of these mountains were at the bottom of the sea. It's hard to believe.
We have similar evidence from Tibet, where we find things like this, ammonite fossils of marine creatures at now more than 4,000 meters above sea level. Certainly these tell us that plate tectonics supplies enough force to lift things from the bottom of the ocean all the way to here, the top of the world.
This is the only place where two continental plates are colliding on such a scale, and the mountains are still growing as a result of the tectonic squeeze. Even Everest is still stretching skywards.
I can't quite feel it just standing here on a piece of Himalayan rock, but my research and the research of the University of Colorado team setting up a network of global positioning system stations all over Nepal, they're telling us that the Earth that I'm standing on is actually moving up at about 10 millimeters a year and is moving to the north at an even faster rate than that, maybe 15 millimeters a year. The reason why we can measure this is because of these fantastic receivers. They use 4 satellites up in the sky above me to solve a simple triangulation problem, but they're so accurate that they can give me something like 1 millimeter of accuracy in the horizontal and more like 5 millimeters in the vertical. That way I can come back year after year. We can see that this point drilled into this rock that's attached somehow to the root of these mountains and the continental plate that they're stuck to is moving.
There is another way that Rebecca Bendick and her colleagues can discover exactly how the Himalayas are growing. They have found an area in the foothills, 10 miles south of the highest peaks, that is rising even faster than the mountains. The clues to the uplift are found in the fast-flowing rivers that tumble through these valleys.
You can think of this river in 2 different ways. One is that this land is still and the river's cutting down. The other way, and I think a better way to think about it, is that the river is staying at sort of a constant position with respect to the sea, way off in the Bay of Bengal, and the earth around it is rising up. So in order for the river to stay in one place, it needs to cut down, like a knife, through butter.
But in some places, the river cannot cut quickly enough to maintain its natural equilibrium. Here, the land rises faster than the river erodes it down, and a giant step is formed, creating white water and rapids.
We're looking for places where the river is a lot steeper than its average gradient anywhere along a stretch. Those steeper places are corresponding to places where the uplift is quick, so quick that the river can't keep up. This will give us clues about places to come back and do more intensive GPS research to try to pin down the uplift rates.
It seems this area is continuing to rise faster than the high peaks. One day, this riverbed will be taller than Everest.
Taking data in this way is dangerous, but with a little bit of care, it's definitely worth the good information that we get about the Earth.
That information is vital for the 100 million people living in the danger zone round the Himalayas. Earthquakes are common. 30,000 people have been killed in the last century alone. This area has been quiet for 700 years, and a major quake is long overdue. Rebecca Bendick's monitoring shows that the convergence of India and China at 2 inches a year is setting up immense stresses which must eventually be released. A solar-powered GPS station will send back information 24 hours a day, hopefully giving an early warning.
The crux of the matter is that we need to know how that total convergence is partitioned over the faults. If all 60 millimeters of convergence has to be accommodated in one place, on one fault, on this one narrow line, then the earthquakes we have there are going to be big and they're going to happen often. But if instead all of that strain is accommodated on several different faults, something like an accordion, then each fault can only be expected to fail less frequently and less violently.
Earthquakes are appallingly destructive to human life, but for scientists, they have their uses. The seismic waves are like sonar. By listening as they pass through the Earth, a picture can be built up of a place no one will ever see. First, the waves race through the crust, the skin on the planet's surface. In some places, only 4 miles separate us from the intolerable heat of the mantle and interior of the Earth. The temperature is nearly 3,000 degrees, so intense the rocks are partially melted. 3,000 miles down in the core itself, the temperature reaches an unimaginable 7,000 degrees. It is the ultimate nuclear reactor, the engine driving the planet. Cooling comes by gigantic convection currents in the mantle, and it's that heat rising with the hot magma that forces the tectonic plates to spread apart. Until recently, scientists had never visited the place where this spreading occurred. It was hidden under the waves. But now even the depths are giving up their secrets. Alvin, the world's first deep-sea submersible, led the way to this unexplored terrain.
Atlantis Alvin, the valve is open, the light is on, the hatch is shut, oxygen's on in this purpose.
One of the first regions visited was the East Pacific Rise, part of the spreading area called the Mid-Ocean Ridge. They expected to find evidence of the Earth at work. What they actually discovered lay beyond imagination. From this pioneering work, scientists worldwide are able to study the extraordinary geological systems 4 miles beneath our feet. Lindsay Parson heads a team at the Southampton Oceanographic Centre.
These are really some of the most amazing images that I think we have of the ocean floor. They're taken from about 3,000 meters down. They're in the deepest, some of the deepest parts of the ocean floor. And we're here looking at hydrothermal systems where bottom water of the sea is being sucked into the ocean floor, is being heated from the heat engine inside the Earth, and is being delivered out into the ocean floor again once it's dissolved and leached out minerals and chemical compounds from the rock itself, which is why the smokers, as we call them, are black and densely colored here.
The pressure is an immense 2 tons per square inch. Water is superheated to over 700 degrees. It's highly acidic, full of hydrogen sulfide and heavy metals. The equivalent volume of the world's oceans is siphoned through the vent systems every 30 million years. Samples prove that the sea floor along the ridges is the youngest on Earth, endlessly reborn. But an even greater surprise lay in store. Even in this harshest of terrain, life takes hold. The black smokers are warm water oases around which familiar species, shrimps, foot-long clams, and mussels thrive alongside more bizarre forms, 6-foot-long tube worms and strange fish.
The majority of the life forms here depend not on light to maintain their existence. They absorb and fix chemicals from the hydrothermal vents to keep them alive. They are chemosynthetic communities rather than photosynthetic communities.
Accurate mapping of the sea floor is now possible and crucial to understanding the system on a grand scale. By careful monitoring, scientists can calculate just how fast the sea floor is spreading and the plates moving. A sonar sledge is towed across the ocean bed. Individual snapshots are processed by computer and a photomontage created. That information is turned into three-dimensional maps. What emerges is that the sea floor is full of great valleys and deep trenches, and that here is the largest and tallest range of volcanic mountains on Earth, 40,000 miles long, sometimes 5 miles high, stretching around the globe like a seam on a baseball. Oceanographic research is difficult, but there is a country that might have been designed as a geological laboratory, the one place where the mid-Atlantic ridge becomes exposed on land. Iceland. The land here is being torn apart. The rift shows exactly where the plates are being forced away from each other at about an inch per year. And Iceland is in the middle. The land is continually reshaped through eruption and rifting. The lava from the flows forms vertical dikes and horizontal beds, just as it does on the ocean floor. Geysers and mud pools are evidence of the heat and pressure just beneath the surface, continually seeking a way to escape. The glaciers inch forward, and a new ice age seems to wait in the wings. Ice and fire is a deadly mixture. In 1996, part of the mid-ocean ridge erupted under the ice cap. It rapidly melted its way through 300 feet of ice, forming a deep gorge. The meltwater raced away to fill a subglacial lake until it could no longer be contained. In the catastrophic flood that followed, 10 square miles of land was drowned. This time, the damage was only to roads and bridges. But in Iceland, the earth is always menacing. In 1975, the Krofla volcanic eruptions began, lasting 9 years. 14 square miles of basalt spewed out, in some places widening the land itself by 28 feet. In 1973, the town of Jaime was almost overwhelmed when the nearby volcano woke from a 5,000-year sleep. 5 months later, the lava and ash had destroyed 300 houses, reshaped the harbor, and added nearly a square mile of new land. Living in a laboratory can be hard. But if new land is continually being made at the crust factory along the ridges, why isn't the world itself constantly expanding? The reason is subduction, the giant recycling process that has been going on since the world began, and which causes most volcanoes and earthquakes. Subduction zones are the graveyards of the old, dense oceanic floor. Where it collides with the lighter continental crust, it's forced down. It pulls the rest of the plate with it to be melted in the ferocious furnace of the inner Earth. The plates don't die peacefully. They go with a bang. The old ocean floor carries water into the mantle, which mixes with the magma. When the pressure can no longer be contained, it explodes. In that most awesome of natural events, a volcanic eruption. Most of the world's volcanoes are in subduction zones, but there are exceptions. Kilauea is on the big island of Hawaii, part of a chain of islands in the middle of the Pacific Ocean, thousands of miles away from any subduction zone. But the whole chain is formed entirely from volcanoes, whose rivers of fire heave and bubble at temperatures of 2,000 degrees. What provides the furnace for all this outpouring if it's not the crashing of the tectonic plates? The volcanologists have an explanation.
The lava that's flowing and spattering behind me is a surface manifestation of a thermal anomaly, or a hot spot that's deep within the earth beneath my feet. Where we are now on Kilauea volcano on the big island of Hawaii is at the southeast end of a 6,000 kilometer long chain of seamounts and volcanic islands that have formed as the Pacific plate has moved north and westward over the last 80 billion years or so at a rate of around 9 or 10 centimeters per year. So as the plate moves over this hot spot, you burn through the lithosphere, forming a volcanic island, and then the plate moves on, and a new island forms further to the southeast.
The hotspot has made Kilauea the tallest mountain in the world, 30,000 feet from its base on the seafloor, taller even than Everest.
Behind me is a perched lava pond that's being fed from a vent off to my left. You can see that there's lava spattering and overflowing on its edges. I'm going to attempt to scoop a sample of molten lava, hopefully with a hammer, so I won't have to use a long cable to throw it in. And it'll be extremely hot. We have to worry about gases, and we have to worry about breakouts near the edge of the pond. So we'll see how it goes.
Thornber is risking his life. But unless scientists can learn how to forecast eruptions, volcanoes will continue to be an uncontrollable threat.
Okay, we'll take this sample back to the USGS Observatory and we'll prepare it for chemical analysis. The chemistry of Hawaiian basalt is unique compared to volcanic deposits near subduction zones or near mid-ocean ridges, and that will be reflected in the chemistry that we see. More importantly, we're looking at very subtle variations in chemistry that can be correlated with the eruptive history of this volcano. So it will allow us to predict what may happen next.
High on Maui, the next island in the chain, NASA scientists at the Satellite Laser Ranging Station are preparing for a long night's work. They're setting up to fire a laser beam at a satellite target orbiting the Earth. The information they gain will tell them to the inch how fast the island and the Pacific plate on which it rests are moving across the ocean. They have to time the firing exactly to be sure that no planes are passing. The laser beam would blind any pilot who might look at it directly.
Okay, we're at 227 azimuth, 18 degrees L. This is starlit. Culmination's at 74 degrees. We're rotating clockwise.
Okay, you'll be clear to fire.
We're at 21 going down.
The laser beam flashes out and bounces back, pinpointing their location. 22 years of calculations confirm that Maui and the Pacific Plate are moving northwest at the rate of 2.5 inches a year, amazingly fast. This is the absolute proof that the surface of our planet is in constant motion. Tectonic theory says that the volcanoes of the Hawaiian chain should get progressively older and become more eroded the further they travel from the hotspot, and they do. One day, the raging fires of Kilauea will be as silent and cold as these dead cones. But the heir to them all is already emerging. As one island dies, a new one is formed.
The hotspot is currently moving or manifesting itself at Loihi, which is a submarine seamound to the south of the big island of Hawaii and still more than 3,000 feet beneath the surface of the ocean. Maybe another 100,000 years before we see Loihi surface.
At the same time, the hotspot is causing destruction elsewhere. The pressure of the continual input of magma from below is bulldozing open this great crack which stretches across the length of the island. It is more than 80 feet deep, and it's splitting away at 3 inches a year. Eventually, the whole side of the mountain will fail and collapse into the sea. It will send a giant wave racing away to the Pacific Rim to reach the west coast of the Americas in a few hours, causing massive destruction. We can't predict or prevent these catastrophes. The fragile truce between man and the earth is being broken all the time. Earthquakes are a ferocious manifestation of the grumbling power of the Earth's tectonic plates. More than 1.5 million people have been killed by them in this century alone. Most quakes occur along fault lines where the plates grind together, but scientists can't tell us when this terrifying destruction is likely to occur. They can only tell us why.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with one foot on one tectonic plate and one on another.
In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
Faults are places of great danger, but they are also geological safety valves.
The fault is the place where two plates slide past each other. If the fault slides smoothly, you don't get earthquakes, but if the fault gets stuck, inevitably you get earthquakes.
At this part of the fault, the plates are stuck. They should be moving at 2 inches a year. The last earthquake was 100 years ago, and the fault is storing up the unreleased energy. The longer the plates are stuck together, the larger the ensuing tremor will be. Further north, the plates are sliding smoothly past each other. The evidence is clear from the way this fence has buckled.
We're on the San Andreas Fault south of San Francisco, and this is an interesting part of the fault zone because the 1906 earthquake ruptured through this field here across the road and stopped about here. But this fence was built after the earthquake. In other words, the fault has been sliding ever since then. So one of the interesting things about this is
what's going on here exactly. And you can see here, there are cracks in the road. These have grown since I was last here, all over the road here. And I have a machine in the field, and I am absolutely dying to see what it says. Let's go have a look. What we have in the field here is a creep meter. A creep meter measures creep on the fault, the creep that's caused the offset of this fence. It consists of a rod that is attached firmly to that side of the fault, passes through the fault into a box here. Inside the box is a computer that's been measuring things. Now, I have to be rather careful because sometimes there are snakes here. Oh, not this time. Good. What's left are black widows and ants. All right. So here is a computer that's been measuring for a year. It records the movement of the fault every minute to about 1/1000th of an inch. So let's download the data and have a look. There we are. Well, it looks as though we've had about 7 millimeters of creep, like this site usually has. But the interesting thing is it's all limited to a very short period of time. If you look here, you can see the fault has been locked for most of the year, but suddenly, in the middle of September, it takes off and it slips about 5 millimeters in the space of a couple of hours, and it continues to slip in the next few days. In other words, a whole year's budget of slip occurs within the space of a few days. That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field, there aren't any people, but further north, this creep process and the things that are happening beneath the earth are far more sinister.
San Francisco is home to 2.5 million people and lies right on the Hayward Fault. In its 200 years history, it's been hit by 3 killer quakes. Scientists know the slippage on the fault has begun to slow down, a warning sign. But when will it strike? In 1989, 67 people died in an earthquake at Loma Prieta, part of San Francisco. No one had foreseen it coming.
Earthquakes are an inevitable consequence of the movement of plates. We cannot stop plate motions, and therefore we cannot stop earthquakes. But we can begin to live with them. And the first thing we must learn to do is to build our cities better.
As the world population grows, so does the danger. There are now more than 100 cities around the world with population of over 2 million, and more than half of those are on plate boundaries or places where earthquakes have already struck. Los Angeles is the most vulnerable of all the places on the West Coast fault line. This stretch of road shows why. Not only is it on the San Andreas, but here the fault is being forced round a bend. Where this happens, the rocks get compressed with enormous force. They cannot go sideways, so they go up. The movement curls the rocks, bends, folds, and crunches them, faulting and distorting the land. Many faults never surface, although scientists know they're there. Known as blind faults, they are probably the most dangerous of all.
You come down the hills here until you hit the plains, the flat area where 11 million people live, and across there, far behind the tall buildings of downtown LA, we think there's a fault right there, right underneath the center of LA.
At 4:24 in the morning on the 17th of January 1994, the suburb of Northridge was shaken to its foundations. A blind fault had fractured 11 miles down, causing some of the most intense ground shaking ever recorded. Ground acceleration exceeded gravity, throwing buildings, furniture, and people into the air. 61 died, 9,000 were injured. Buildings, roads, and bridges were destroyed. Damages ran to $20 billion, and the aftershocks went on for days.
two things an earthquake can do. When it goes, like Northridge did, seismic waves are spread all over the basin. There's big ripples shaking all the buildings. Everyone feels it. But there are certain locations where the shaking is much worse. And that occurs through a process of seismic waves that are reflected from the mountains. It's exaggerated where the sediments are concentrated in the basin here, because the basin is completely flat, and it's flat because it's washed in there from the mountains by water. So we have saturated sediments.
When the sand and water combination is shaken together, as in an earthquake, it turns liquid for 5 minutes after the shocks, causing tall buildings to destabilize and fall. It's called liquefaction and presents an enormous and unpredictable danger. And there is another geological trap waiting to spring. The San Gabriel Mountains stretch from the San Andreas Fault down to the Los Angeles Basin. As the earthquakes crack and shudder along the faults, they are being inched towards the city. Here the fault is pink and the mountains in yellow. This is how they have swung so far. In some distant geological future, they will cover the city completely. What does the geological future look like? What clues are hidden in the mountains, deserts, and seas? Human time span is so short, it's hard to understand that we will be undone by forces that play out over millions of years. It's difficult to grasp that the march of the Earth is unstoppable.
We've been very lucky because modern society has actually developed at a time when very little has been happening geologically. So we've been in a period of geological quiescence. Now this isn't going to last. We know that there are going to be major global catastrophes occurring in the future, gigantic tsunami, big volcanic eruptions, more impact events. And on that basis, we know that we're all living on this planet simply by geological consent.
Ice is crucial in helping to keep the Earth's climate mild enough for life to survive, but worldwide the temperature is rising and the ice is melting. If this keeps happening, sea levels will rise. A rise of only 15 inches would spell catastrophe for low-lying countries and low-lying cities.
Major sea level rise in itself may be catastrophic for the planet, but actually there are unexpected effects as well, and that is that rising sea levels may trigger volcanic eruptions. We know this because we've been looking at the relationship between changing sea levels and volcanic eruptions in the Ice Age, when we had changes of 100 or 200 meters in sea level over a few tens of thousands of years.
Maguire's new work on Etna seems to show that the more rapidly sea level rises or falls, the more violently the volcano tends to explode.
When sea levels rise around coastal volcanoes such as Etna, they have a rather interesting effect. If you imagine the volcano sitting on a plate with Etna here, if you then load the other half of the plate by sea level change of 100 meters or so, it has the effect of bending it. And what that does is set up tensional stresses within the volcano, and any magma sitting there will burst its way out in the form of an explosive eruption.
In modern times, we haven't really experienced the full terror of a volcanic catastrophe. If Bill Maguire's theory is right, such an event could hurry in the new ice age, because nature can wield a two-edged sword. Rising sea levels could cause volcanoes to erupt, spewing debris and sulfur into the atmosphere. That will cut out the heat from the sun, so the Earth will cool. That will make the ice form again, freezing the oceans so sea levels drop once more. And that sudden fall may trigger more volcanic activity, pumping more material into the atmosphere, making the Earth even colder, ushering in the dark